Yeah, it's clear. We can hear you.
Can we start right now?
Yeah, sure thing. Uh, the stage is yours.
Okay. There's no one in the waiting room. Have we wait for just 3 or 5 minutes, or start right now?
I think it's better to start right now.
Okay. Thank you.
Uh,
Okay, hello everyone, and welcome to this online webinar of reserve classifications and estimation techniques. I'm Hisham Mukhtar, Senior Reservoir Engineer from Cairo, Egypt. Today is January 28, 2021. I hope this new year is will be happy for all of you, and it will mark the end of COVID-19 throughout the world. So right now, your attention please. Let's start directly with our agenda today. We'll start with introduction, and after that, what is the BRMS, or Petroleum Resources Management System, definitions, classifications, and terminology, difference between deterministic and stochastic reserve estimation techniques. And after that, we will highlight the different estimation techniques, starting with the volumetric technique, and after that, performance-based techniques like decline curve analysis applications of Schlumberger of M, and after that, the generalized or conventional material balance analysis, the main concept and general form, and then the more advanced form of the material balance, or the dynamic material balance equation, what is the definition and procedure, and finally RTA, or rate transient analysis procedure, and different definitions and applications of Cabatobas software. Now, and at the beginning, I'd like to highlight what is the RE, or reservoir engineering. How does it work? Simply, the reservoir engineering is a branch of petroleum engineering that's concerned with the applications of fluid flow in the porous media in the subsurface reservoirs during the production and development of oil fields. The main objective of this discipline typically is to maximize the hydrocarbon recovery throughout the oil field lifetime. So in RE, we have three main fundamentals typically used in all reservoir engineering applications. The first one, the widely used in all applications, is Darcy's law of flow rate equation. As we have a fluid flow in a porous medium, so we have to apply flow rate equation. The second one is the continuity equation, or material balance equation, simply because we have a specific volume or subsurface volume of storage. Therefore, the remaining volume will be the initial volume minus the produced volume. The last one is the equation of state, or BVT model, because the properties of reservoir fluids like oil density, oil viscosity, or formation volume factor, and so on, are typically dependent of pressure. And during the development of oil reservoirs, the pressure declines from the initial or average reservoir pressure to the bottom hole flowing pressure, or BWF, and then to wellhead pressure. So we have to apply equation of state, or BVT model, to characterize the properties of reservoir fluids while production. For the complete system analysis, we have to integrate, or to, add additional two models that are the inflow and outflow performance model, IBRO and VLP models. So, what is the meaning, or the core of reserves? The term reserve is typically is something saved for future needs or specific purpose. For the bankers, the term reserve means the capital retained to meet the probable future demands, while for oil and gas operators, reserve means the volume of the hydrocarbon we have in the subsurface reservoirs that can be recovered under existing economic and operating conditions. By integrating a specific economic model, which means we have specific capital and operating costs, oil taxes, and oil prices, finally we can get the net present value of the project and net present value of hydrocarbon volumes that we have in subsurface. Therefore, the term reserve is finally means the value or the economic value of hydrocarbon product we have in the subsurface reservoirs. Why we need to define the reserves? Because all input parameters used in reserve calculations contain inherent uncertainty. So it's important to set standard definitions, standard terminology to quantify the level of uncertainty. Typically, we have two different types of uncertainty. The first one is the physical uncertainty related to the subsurface reservoirs or reservoir properties, reservoir heterogeneity, reservoir thickness, reservoir extension, driving mechanism, and so on. And second one, the second one is the commercial uncertainty. The commercial uncertainty is typically related to the CapEx, OpEx, and the prices. CapEx is simply the cost for exploration and development. The OpEx or operating cost, the cost for production, processing, and transportation. And prices is the market value of the hydrocarbon product we have, maybe oil or even gas condensate or dry gas. So it's important to set standard definitions for reserve and common terminology for global reserve discussions. So why we have to estimate reserve? Different segments typically are concerned with the oil and gas industry. So it's important to identify how much oil we have in the subsurface reservoir. It's important quantity for the oil and gas company, for the bankers or investors, for the taxation or regulations company, for the governments. It's important to calculate or to identify how much oil and gas we have in subsurface reservoirs. Also, based on the value of reserve we have, different parameters will be dependent of the estimated reserve, such as the sizing and designing of processing and transportation facilities, the assigned field development plan and predicted production profiles, the assigned budget or cost for the applied project, and finally it's important to identify the key uncertainties in the calculated or estimated reserve. So as you can see, we have different interests in oil and gas reserves. The first interest is for the oil and gas operators, oil and gas companies. They are interested to maximize return equivalent to proved reserve, or 1B. B50 is a reserve at 50% probability, or 2B equals B plus B proved plus probable. B10 is reserve at 10% probability, which equals to 3B proved plus probable plus possible reserve. We typically have two different techniques for calculating or estimating reserve. The first one is the deterministic approach. Deterministic simply means we have single value of the input parameter used in the calculations. The input parameter typically are geological and engineering data. Deterministic is usually known as the 3-point estimate, low, best, and high estimate. Second approach is the probabilistic or stochastic reserve estimation technique. In this technique, we have a set of range of the input parameter with the corresponding probabilities. Simply in deterministic, we have Q production, which is calculated, which is measured, and then at 1B scenario, we have proved reserve, 2B scenario, proved plus probable, and 3B scenario is proved plus probable plus possible reserve. And at this point, we have EOR, estimated ultimate recovery. While stochastic reserve estimate, as you can see, we have this distribution function of probability of value. And in x-axis, we have estimated ultimate recovery. At 100% probability level, we have Q production. So this value is already reduced. So we have 100% probability and zero uncertainty. At 90% probability, we have 1B or proved reserve. At 50%, as you can see, we have 2B. And at 10%, we have 3B or B10. Again, this is an example. If we have this input parameter like net rock volume, average porosity, and the corresponding distribution. For example, this distribution for porosity, coordinate water saturation. We have triangle distribution for this parameter, formation volume factor, this corresponding distribution, and recovery factor. So by multiplying all of these parameters, we will get this final distribution like this. And at 90% get B90 and 10% probability you will get B10. This is a field sample of reserve reporting. As you can see, it's a visa report as of January 31, 2012, as of Aswan poverty in Egypt. As you can see in this report, we have BRMS case. Inside this report, you will find different definitions, classifications, and calculations of reserve. So you will have a set of volumes of reserve. After that, by using a specific economic model to incorporate the cost, capex, and OPEX, taxes, and oil prices. So you will have the values or net present value of the project at a specific discount rates. This is another example for the audit for South Disouq in Egypt. This report statement of the gas report at September 30, 2019. We have this reserve summary for South Disouq gas field. As you can see, we have proved, probable, and possible reserve in values in billion standard cubic foot. And second part of this report is net present value summary. As you can see, at this different discount rates, you will find the net present value of the project, and this is the important for oil and gas operators to have the net present value of the entire subsurface accumulations and entire subsurface volumes or reserve. Simply to simplify the technique, the input parameter like petrophysical data, as you can see, you have this will log in this map, the structure contour map in top of the reservoir. So petrophysical parameter will input to Monte Carlo simulation software like Reservoir to get the range of uncertainty. So as you can see, we have this is the input parameter like gross work volume, formation volume factor, porosity, net growth, and so on, and corresponding distribution function. And we have B90, B50, and B10, minimum, maximum, and most likely value for every input parameter. Finally, the calculated reserve gas initial interest will be B90, B50, and B10. B10 is the gas reserve at 10% probability of the input parameters, and B90 will be the lowest value, while B10 will be the highest value, as you can see. The first category for reserve is the proved reserve. Proved is typically as per the definition of PB just mentioned, can be recovered under existing and economic operating conditions and under governmental regulations. For the proved reserve, processing and transportation facility must be operational. Uh, Also, we have to have high degree of uncertainty or high degree of confidence. Uh, they like to have accurate geological and engineering data and valid assumptions like the formation factors. So for proved reserve, we have to the calculated reserve must be supported by actual production of formation test. And in case of if we have no clear hydrocarbon water contact, so the proved area must be limited to the limit of the lowest known hydrocarbon. As you can see, we have two wells. In well A, we have this oil column. We have oil gradient without clear oil water contact. So in this case, the proved reserve must be limited. This area in green color must be limited to oil down to at this point. And if we have after that, if we have clear oil water contact, so the area will be increased. The categories of proved reserve developed, which means recoverable from existing wells, two classifications for developed producing, which means it's recoverable from the current or open completion intervals. Non-producing is we have maybe shut-in, which means we have open completion, open perforation interval, while the well is closed, waiting for market conditions or waiting for installing production facilities, for example. While behind the pipe, as you can see, the reservoir will require additional completion work in the future. This is a field example for reserve classification. We have testing data for this well in the Gulf of Suez, Egypt. And this is the testing data in Ocean Reservoir. This well is currently shut in because we are waiting the production facility installment. Therefore, in this case, and according to PRMS guidelines, this result is categorized or classified or defined as proved. Proved because we have actual formation test. This data developed because we have a specific active well. Non-producing because we have waiting the well is currently closed, waiting the installing the facility, and shut in because the well is currently the perforation is currently shut in. Probable reserve is certain than the proved reserve by definition. As you can see, maybe area is geologically separated by faulting like this, and higher in structure, this is proved, and this area higher in structure than proved area. So this area can be classified as probable reserve. Possible reserve by definition are less certain than probable. And we have low degree of certainty in the input parameters. An example for this is to have this area just geologically and structurally separated by the proved areas you can see by this fault, and lower in structure by lower than the proved area. So these areas you can see on the left hand side of this fault will be classified as possible reserve. We have different project maturity subclasses. You can see we have prospective resources, contingent resources, and reserve. It's important to know the subclasses of the prospective resources. We have play, lead, and prospect. The most important term in this subclasses is the prospect. Prospect, by definition, is the most commercial part of the prospective resources. Simply, it's the potential accumulation that can be a reliable drilling target, uh, can be seen on the seismic processing. So the prospect is the top commercial part of the prospective resources, and is the a good drilling target to start exploration and start drilling operations. Second part in this webinar is to highlight reserve estimation techniques, different techniques. We typically have different techniques like the analogy. Analogy is typically used in pre-drilling phases, because in this phase we don't have sufficient data for reserve calculations. Volumetric typically used in exploration and appraisal phase of the oil field, and the most important, the performance-based reserve estimation techniques. In this technique, we have different production data like flowing pressure and flow rates. So we will use this production data to calculate reserve. Example for this, the decline curve analysis, like exponential, the empirical Arps equation, or even the advanced Fetkovich approach, material balance, static or dynamic, RTA or transient analysis, and finally reservoir simulation. The first technique is the volumetric reserve estimates. I think all of you is familiar with this equation, the STOIB, original oil in place, or N, will be calculated using this equation as a function of E, H, and phi, SWI, and B sub oil initial in units of stock tank barrel. So original oil reserve will be N times recovery factor, and original solution gas in place is N times initial solution gas oil ratio. Simply, the term oil formation, initial oil formation volume factor, this term is used to convert the downhole volumes to equivalent surface volumes, because the volume of oil, for example, will be reduced from reservoir or from downhole to surface due to mass losses because we have more solution gas will be released, while we have reduction in flowing pressure from bottom of the well to the wellhead. This is an field example of the volumetric reserve estimation for oil reservoir. As you can see, we have this well log and the corresponding physical interpretation. This oil reservoir, the area used in this calculation is taken till the oil water contact. But the physical parameter net gross phi SWI is taken from this log interpretation. BVT data like oil formation volume factor, initial value, and solution gas ratio can be taken by analogy or even by valid PVT study. As you can see, we have these values, and finally we have a story. And at specific recovery factor, we have original oil reserve. Similarly, for gas reservoirs, we have a similar equation like this in stock tank barrel, while the widely used equation for gas reserve is this equation. Gas initially placed this equation in units of standard cubic foot. In this equation, you have to have the gas formation volume factor B sub G. It will be calculated by this equation as a function of Z factor, pressure, and temperature in this unit, and this is the typical shape of the compressibility factor or D factor taken by a PVT study of gas sample or gas condensate sample. The second group for reserve estimation technique is the performance-based techniques. First one is the decline curve analysis, or in two parts of this technique, conventional and advanced technique. Simply, the decline curve analysis is an important reservoir engineering technique that used for reserve estimation by matching the past performance, as you can see, to predict the future performance and calculate reserve and get the EUR, or estimated ultimate recovery. The first approach of this decline curve is the conventional decline analysis, like Arps equation. Arps is typically an important analytical empirical reservoir engineering approach. Is used to calculate oil rate as time t as a function of initial rate and b, or hyperbolic exponent the I, which is very important parameter in this equation, in initial instantaneous decline rate and the time for the forecast. We typically have three different forms of this equation based on the value of hyperbolic exponent b. Hyperbolic value of b from 0 to 1, exponential of value of b is 0, and harmonic if b is 1. However, it's important to keep in mind the assumptions of Arps equation. The main assumption is we consider the well is producing at constant bottom hole flowing pressure VWF. In this case, this equation is only applicable to the boundary dominated flow or pseudo-steady state flow. In this animation, as you can see, I will simply discuss the different flow regimes. We can assume we have a vertical well in the center of circular homogeneous reservoir. Initially, if we have no production, so the reservoir pressure will be constant at BI, or have a pressure transient. As you can see in this animation, we have pressure transient is created at the well bore. This pressure transient will be moving in reservoir, as you can see, based on the reservoir properties, like reservoir permeability, fluid viscosity, and so on. So if this pressure transient doesn't reach the reservoir boundary in this red color, so we have transient or unsteady state flow condition. Once the pressure transient is reached the reservoir boundaries, so in this case we have pseudo-steady state flow or boundary dominated flow. So this is the what does it mean by boundary dominated flow? So in this flow regime, the partial B over partial T, or rate of a change of rate of a change of pressure with time is constant. In other words, this means the reservoir pressure will decline throughout the entire reservoir at a constant rate, or we have constant reservoir pressure decline with time. The different analysis plots for Arps equation or Arps technique. We simply have production data versus time, as you can see, rate versus time in normal coordinates. We have different scenarios, exponential, hyperbolic, and harmonic. If we plot this data on semi-log plot, as you can see, log Q versus time, so the exponential decline in this green color, we will have a straight line. Also, if we plot rate versus Q production, as you can see, we will get the exponential decline as a straight line. So as you can see, at any time t, for example, at this point, you will find the exponential decline will predict the lowest oil rate, which means by using the exponential decline, the predicted reserve or predicted ultimate recovery will be the lowest value, or in other words, will be conservative, will be more conservative than the hyperbolic or even harmonic used for oil and gas companies because it predicts the lowest values. Also, because it's simple in calculations, as you can see, because we have the straight line by plotting log Q versus time. Exponential is also known as CPD or constant percentage decline because we have a constant decline rate because we have a straight line. This approach at b equals 0. So this Arps equation will be presented in this form, and estimated ultimate recovery will be defined by this equation. So in using exponential decline, we will have a straight line by plotting log Q versus time, and also by plotting log Q production rate versus Q production. The second type of the decline is on the curve analysis, the advanced decline analysis or Fetkovich approach. And Arps equation, because Arps is only applicable during the boundary dominated flow or the state flow conditions. So it's important to consider the transient flow condition. So Fetkovich used the analytical flow equations in dimensionless formats to develop type curves, as you can see. We have this type curve for Fetkovich, which incorporated the empirical Arps solution in addition to the transient solution to finally characterize the entire period of our well, including the transient and pseudo-state flow condition. As you can see from this type curve, we have two families of curves. The first one is the analytical, or which is Fetkovich constant pressure solution. This families of curves are dependent of RD, as you can see, or dimensionless the Wilbur radius, dimensionless drainage radius, or early time or transient stem. Second group is boundary during the boundary dominated flow are empirical or Arps solution dependent of the value of P or hyperbolic exponent, as you can see from 0 to 1. Main outputs of advanced decline analysis are the reservoir parameters like the reservoir permeability and skin, and reserve, and finally the EUR or estimated ultimate recovery. In this type curve, we can add the cumulative curve Q production with the oil rate. You have this family rate versus time on log-log plot dimensionless type curve, and QM reduction. This curve is not available in O of M, while it's available in capital base, for example. So simply to summarize Fetkovich analysis, we have, as you can see, we have analytical or a constant pressure solution. This solution function of RW or drainage radius plus the empirical or Arps equation plotted on log-log plots, function of value of B. Finally, by incorporating the two families together, we have Fetkovich type curve. And now the applications of oil field manager OFM for decline curve analysis applications. OFM is widely used software for reservoir surveillance, production analysis, and reservoir management. It's a software branch of Schlumberger. It's an integrated tool for mapping and trending the production data, production performance, decline curve analysis using Arps and Fetkovich approach, water flooding optimization and pattern analysis, and different applications. Now, it's important to highlight the terminology of decline curve analysis in OFM. As you can see, we have this field data for, we have oil rate versus time versus date. And this is the history production for this well or even the entire field. So at this point, we have history or actual production. And at this point, we have NV or cumulative oil production. While at this point, we have prediction or the predicted future for this well. So in OFM on the decline curve analysis, we will match this the past performance, as you can see, using this straight line, using the exponential approach to predict the future production and estimate the or get the estimated ultimate recovery EUR. As you can see, this is a snapshot of the tools available in OFM. Solution is empirical or Arps equation, decline rate or DI, and the history match for this part of our well lifetime. Fit type is exponential, which means we have the value of B is 0. So as you can see in this results, we have B equals 0. And we have at this point, we have in 2017, we have final rate, this value, and QM production. While the estimated reserve of this value at 2028, and finally the EUR or estimated ultimate recovery, which is the QM production plus the remaining reserve. In OFM, we have different techniques for analysis empirical solution like Arps equation, Fetkovich, and second Fetkovich type curve like this. And Fetkovich type curve, OFM will plot the production data over the dimensionless log-log plot, as you can see, and after that we will match the our data on one of the available curves to get the reservoir parameter and to calculate the reserve and estimated ultimate recovery. Also on OFM, we can save our forecast and we can make different oil schedules corresponding to different oil scenarios equivalent to P90, as you can see, P50 and P10. So this is an example, field example for Fetkovich type curve applications. In this example, we have this production data in red color, and this is the Fetkovich type curve in log-log plot, dimensionless orbit, and this is dimensionless time. This curve will be used to identify the probable value of B or hyperbolic exponent. As you can see, this for this well, the value of B is not 0, but it's 0.25. So we can use the Fetkovich type curve to identify the correct value of B rather than the value of B equals 0. As mentioned, we usually use B value as 0 because it's more conservative and we will predict the lowest value. However, if you need to identify the correct value of B, so we can use Fetkovich type curve and see the probable value of hyperbolic exponent B. Second technique is the third technique is the material balance equation. Simply, the material balance is an important and analytical reservoir engineering technique used for reserve estimation. Material balance is typically a relationship between reservoir pressure, reservoir pore volume, and cum production. So as you can see, if we have this reservoir, we have this initial condition, and with production, we have oil produced versus time, and this we may have gas injection, water injection from for oil, for water aquifer, and so on. So the main requirements for the material balance applications are the production data are NB, RB, WB, and GB. Cum oil produced, cum gas produced, cum water, and cum produced gas oil ratio. Second requirement, the accurate determination of average reservoir pressure, and finally, BBT data like oil formation volume factor, rock compressibility, and so on. So applications of material balance is to estimate the STOIIP N or G, oil initially in place or gas initially in place. Estimate the WE or water influx, M gas cap volume. Also, it's very important tool to identify the production mechanism or driving index related to the active production driving mechanism. Simply, material balance is the total change in reservoir volume will be the change of reservoir gas volume plus oil volume plus water volume. So the initial stage, as you can see, we have oil, gas, and water at initial reservoir condition without production. Once we're starting production, we have production of oil, water, and gas. If we have a injection, or we have gas or injection of water, and the final stage, because we have changes in production, injection of gas or water, and so on. So due to change in pressures and volume, so we will have changes in oil and water and the gas saturation in our reservoir. Now it's important to know the main assumptions of material balance equations. First one is very important. Material balance is typically a zero dimension or tank model, which means the entire reservoir is considered as point. This means we consider the reservoir has a uniform reservoir characteristics like porosity, thickness, different reservoir properties are considered as consistent or uniform. Also, we consider we have a pressure stabilization or pressure equilibrium throughout the entire reservoir. Simply, the general material balance equation is states that the withdrawal or production equals expansion of oil and solution on liberated gas, or in other words, the reservoir volume of oil, water, and gas production will equal the expansion of oil and free gas initially in place. Simply, for example, we have withdrawal in oil production in the reservoir barrel, as you can see. So we have NB plus RB plus WB, cum oil, cum water, and cum gas production. For example, for oil expansion in the reservoir barrel, this system is N, or initial oil in the stock tank barrel, times this term, which is expansion B sub O minus B sub O initial net oil expansion in the reservoir barrel. So it's very simple to understand the generalized material balance equation. However, if we consider the simplest form of material balance equation as the following assumptions, if we consider the average reservoir pressure higher than the saturation or bubble point pressure, so in this case, RV will equal RS oil initial or RSO, because above the bubble point we have no gas, no free gas in the reservoir. Second, if we have no gas production, so GB equals 0, WB equals 0 for no water production, no initial gas cap, so M equals 0. M is the ratio of gas cap to oil zone volume. If we have no water influx, so WB equals 0. So the simplest form you have to keep in mind, this equation must be clear for all of you. Withdrawal equal expansion, so NB times B sub O will equal N times this term. So the recovery factor will be N over NB over N, this term of the oil formation volume factor. This is the simplest form of the material balance equation, and exactly you have to keep it in mind. This based on this concept of withdrawal equal expansion. Simply because we have a complex form of the material balance equation introduced in 1941. So in 1964 and 1963, Havlena-Odeh presented in a more similar form of the material balance equation by rearranging the general equation and to present a equation of a straight line. This approach is simply based on the plotting a group of variables versus another variable to get a straight line form based on the reservoir driving mechanism. Simply, this general formula of Havlena-Odeh material balance equation, we have this left-hand side F representing the production of oil and water and gas, as you can see, in reservoir barrel. This is typically similar to the general form of material balance equation. While this right-hand side, we have the expansion term in the reservoir barrel, the stock tank barrel, expansion of oil and solution gas, E sub O, expansion of oil and solution gas, E, F, and W, expansion of formation and condensate water, and last one, E sub G, or expansion of free gas. And this is the equation for all of them. And finally, this is the general straight line form of Havlena-Odeh material balance equation. So if we consider we have reservoir, so This is the general form. So in this reservoir, we have no initial gas cap, so M equals 0, no water influx, W equals 0, and neglect EF and W. So in this case, F will equal N times E sub O. If we present this equation as a straight line equation, so we'll have y equal ax plus 0. So it's a straight line equation in f on y-axis versus e sub o. The slope of this equation will be n or stoic, and the intercept will be 0. So for depletion drive, by plotting f versus e sub o, you will find n or stoic is the slope of this straight line, just that passing through the origin, according to this straight line equation. Another example, if we have water influx, this is the general equation of Havlena-Odeh as material balance. So we M equals 0, we have no gas cap, we neglect E, F, and W. So we will have this form. So in this case, the most uncertain parameter is WE, or water influx. In this case, we have to have a water influx model to predict WE, or water influx, as a function of pressure and time. We typically have different water influx model like Carter and Tracy, Fetkovich, House, Van Valdingen, and so on. By rearranging this equation, as you can see, F over E sub O, we will have this straight line form in y-axis and x-axis. According to this equation, you will have a unit slope straight line A, as you can see, and the y-axis intercept will be n or stoic. So it's very simple by using a straight line equation, material balance equation, in case of water influx. And now we highlight the applications of IM material MBAL software for material balance analysis. Typically, MBAL software is used for applications of material balance analysis based on the tank model. In MBAL, after defining the reservoir model and loading the production and pressure data, the most important step is the history matching. The history matching in MBAL typically involves two complementary approaches. The first is the analytical approach. Analytical means the matching the tank pressure versus fuel production using regression analysis. As you can see, we have regression analysis. In this case, we have to select the most uncertain parameter like WE, water influx, M, and so on, as the matching parameter and run the regression. The second approach is the graphical approach. By plotting different diagnostic plots, as you can see, typically based on the straight line form of material balance to used a graphical approach will be used to calculate or validate the results of analytical approach. We have just a field example for this reservoir with volumetric depletion. We have production data versus time. And this reservoir, we use this equation F equals N times sub T, as you can see. By plotting these two terms together, the slope of the line will be n, the intercept will be 0. So as you can see, according to this equation, n will be 50 million stock tank barrel. But in reality, we have a small water aquifer, so This value of n will be higher than expected by this straight line, as you can see. So n in this case will be more or less 57 million stock tank barrels because we have a small water aquifer. This is another example of MBAL software. In this, we have oil reservoir with or without the water aquifer. The analytical analysis, you can see we have tank pressure versus cum oil production, and this is the field data or actual production data of tank reservoir pressure versus cum production. As you can see, we have two scenarios with aquifer influx in blue color and without aquifer influx in red color. As you can see, the data shows good fitting using the model of aquifer influx. So in this case, the value of oil in place is 46 million stock tank barrel. And using graphical approach, using this F minus W, as you can see, versus E sub T, and according to this equation, so the value of n or stoic will be the slope of this line. As you can see, it's about 42 million stock tank barrel. So we probably have the value of n or oil in place is more or less 45 million stock tank barrel based on the analytical and graphical technique in MBAL software. The next is the flowing or dynamic material balance equation. As the name implies, this approach is will cover the limits of the limitations of conventional material balance or static material balance equation, because in the traditional material balance, we have to shut in our wells at several points during production to get accurate estimation of the average reservoir pressure. However, using flowing material balance, we can get accurate determination of reserve without shutting our wells, without the loss of production. Flowing material balance is effective way to get the estimated reserve. And this technique, we have no type curves. It's typically analytical technique. As you can see, this technique is applicable during the boundary dominated flow, as mentioned before. And the boundary dominated or pseudo-steady state flow, the reservoir pressure, as you can see, will decline throughout the entire reservoir at the same rate or at the constant rate, because partial V over partial T will be constant. A very important parameter in flowing material balance is the material balance time. This term is used to convert the variable rate production scenario to the equivalent constant rate production scenario. Simply, as you can see in actual production, we have a decline in oil rate versus time versus flowing time, actual rate decline. However, in flowing material balance, we have to use the constant rate solution. So the flowing material balance will be used to get the equivalent constant rate. If we use a constant rate, this term, flowing material balance, is the calculated time or the material balance time to get equivalent cum production in case of constant rate solution. For all the flowing material balance, by definition, equal in NB over Q sub oil rate, the cum oil over the oil rate, while for the gas reservoirs, the flowing material balance time will be the material balance pseudo time, because in case of gas reservoirs, the gas properties like gas density, gas viscosity are typically highly dependent of pressure. So in this definition will be replaced by this equation. So again, the material balance time is the time used to convert the variable rate production scenario to equivalent constant rate production scenario, and it's the time required to produce the same cum production using a constant rate equivalent to the cum production using a variable rate. Simply, the flowing material balance is dependent on the definition of the isothermal compressibility. As you can see, the rate of a change of volume with pressure relative to the initial volume. As you know, the initial volume is N, or the story. So we can apply this equation again to get this for, and combining and rearranging and introducing the material balance time, we'll get this equation. Simply, this equation have two pressure loss components: pressure loss due to depletion and the pressure loss due to inflow. Because during production we have the pressure losses inside the reservoir and the pressure losses from the during the flow across the perforated intervals. So in this case we have the two different pressure loss components due to depletion and due to inflow. This is the definition of pressure loss due to depletion, this equation, and pressure loss due to inflow. BI minus average reservoir pressure is pressure loss due to depletion, and BR minus BWF, because we have pressure loss due to inflow across the perforated or perforations. So after that, if we plot delta B over Q versus time, as you can see this plot, we will get this term B sub BSS, or the pseudo-state constant. This term will be used to calculate the average reservoir pressure while production. So the flowing material balance is simply used to calculate the average reservoir pressure while production, without the need of shutting the wells, without the loss of production, and without the need to close the some wells during the oil field development or during the production lifetime. So average reservoir pressure will be calculated using as a function of BWF, oil rate, and state constant, this term. Finally, we can plot Q over delta V versus this term in x-axis. The x-axis intercept for this equation of this relationship will be N, or original oil in place. To simplify this approach, this is a field example for this. For oil well, as you can see, we have oil rate versus time, flowing rate versus time, and flowing pressure, bottom hole pressure versus time. The first step is to plot delta B over Q versus material balance time. As you can see, we have this data. We will use the data of boundary dominated flow, this stabilized data, as you can see, to get the value of BSS, or so the steady state constant. That will be the y-axis intercept. After that, the next step is to calculate the average reservoir pressure using this equation, and finally plot this term on y-axis Q over delta B versus this term on x-axis. As you can see, the x-axis intercept will be n or stoy. So in this example, or this field example, n is more or less 55 million stock tank bag. The last technique in this webinar is the RTA, or transient analysis. Is typically an extension of PTA, or pressure transient analysis, usually like different reservoir engineering tools. This technique combines Darcy's law equation of state and the integral balance equation to present partial differential equation that will be solved analytically to calculate the reservoir parameters and calculate reserve. Topaz software is typically used for RTA. Topaz is one of the modules of Kappa orchestration. This software will be used to analyze production data to calculate the reservoir parameters and calculate reserve and estimated ultimate recovery. In Kappa we have, as you can see, we have different analysis tools like Fetkovich type curve, which is similar to OFM. As you can see, and as mentioned before, in dimensionless type curve of Fetkovich, we have normalized rate Q curve, Fetkovich plot, and log-log plot. Topaz log-log plot, as you can see, it's simply a relationship of log delta B over Q versus log material balance time and pressure integral versus material balance time, and the derivative of pressure integral versus material balance time. As you can see, we have three sets of type curves. What we will do in Kappa is to match our production data on this type curve. So as you can see, we have normalized pressure integral type curve in this green color, and a normalized pressure integral derivative type curve in this red color. Our data is matched using this plot. As you can see, once we have just straight lines, so in this case we have boundary dominated flow, so it will be used to calculate the reserve of our reservoir. And the data of this region or transient flow region will be used to calculate reservoir properties like reservoir permeability and skin. The second analysis tool available for Topaz software is the normalized rate cum plot. As you can see, it's a relation according to this relationship in y versus x. And last one is the Fetkovich type curve, typically similar to OFM, but in Kappa Topaz, this cum curve is available, while in OFM, the dimensionless of rate versus time is only available without the cumulative curves. To discuss this, some field example for RTA, we have flowing pressure versus time and flow rate. If we define a new project in Kappa Topaz using this parameter for velocity and net pay and production data, as you can see, for almost 1,000 hours, load production data, production rate, and pressure versus time. So in Kappa Topaz, you will have this history plot. The next step is to assign a specific model to match the production data of our well on the log-log plot. As you can see, this is the log-log plot. The data is matched over this plot. So we have different properties of our well or our reservoir. And finally, we'll have the value of N or store, as you can see, 23.9 million stick tank barrel. Another tool to confirm the value of N is the normalized rate cumulative plot. As you can see, typically the N is 23.3. So according to this analysis, N is more or less 23.5 million stock tank barrel. So this is the last slide of this webinar. Now our conclusion for this webinar, the PRMS or Petroleum Resources Management System is the oil and gas industry global standard for their classification and reporting. PRMS classifications are from the top commerciality level to bottom are reserves, contingent resources, and prospective resources. The reserve must satisfy four criteria: must be discovered, recoverable, commercial, and remaining. The unproved reserve as classified as probable and possible reserves. The volumetric equation is a basic equation for calculations of oil reserve and hydrocarbons in this. Ours is an analytical and an empirical approach is a quick and simple way to get a reserve and identify the estimated ultimate recovery EUR. Fetkovich type curve is used to analyze both transient and boundary or pseudo state flow periods. Material balance equation is a zero-dimensional tank model and an analytical reservoir engineering approach. Flowing material balance is a technique that provides an easy and effective way to calculate and estimate reserve and hydrocarbons in place. And finally, the RTE or rate transient analysis is an extension of BTE or pressure transient analysis used to get the reservoir properties and calculate reserve. So this is the end of this webinar. Thank you so much for joining me in this session. And now feel free to ask any questions. Yes, any questions? Any
Does
questions?
anybody have a feel free to put it down.
Everyone have a question, you can make raise hand and I'll make you to talk.
So any questions, please? If you